Okay. I hope everybody can hear me as I'm just getting things set up here. It is a really immense and great honor to start out this great conference, and I would really like to thank the organizers for the opportunity and for getting us all together. I think this is quite a feat of showing of strength of pulling people from across the world through this online conference together. And I saw already on the list of people participating, friends and colleagues from, I should also turn on my camera here. Yes, from China, from Japan, from the US, from Iceland, from France, all over the world really. And it's really, this is really amazing. I started out by just putting some pictures up to get an idea of the places that we have done measurements over the last 10 years. So with not much further ado, I will see if I can move this thing here. Yeah. So I gave the presentation the title, A Decade of Continuous Water Vapor Isotope Measurements on Timescales from Seconds to Years and on Local to Regional Scales. And I want to really stress that I'm standing on the shoulders of so many people who have helped in the field, who have helped with data analysis, who have helped with model simulations, who are being there all the time. And so I want to thank you all for that. And specifically, I also want to just say that actually this is also a little bit of nostalgic time, because exactly this week, 10 years ago, I started the Picaro analyzer in Bermuda, where I was a postdoc with a grant from the Danish Research Council to set up a continuous water vapor and precipitation isotope measurements. It was meant to run for 1 year, but it has actually been running for 10 now. So this it was a little bit like when I look back into my files and realized that actually the first file was from this week. So I was like, wow, quite a lot of water under the bridge. But anyway, we should not dwell too much in nostalgia. So this is an outline for my presentation, and I thought it was pertinent to put setting a stage, because there's a lot of new colleagues in the field that has come here for the last 10 years. So I thought it was nice to just kind of say, where did we come from? And as part of that is also understanding calibration development and issues. So I will also focus a little bit on what have led to us being able to make very high quality measurements. I will then go through what I more or less call a medley of water vapor isotope observations in space and time. And what is also important to understand here is that I am confining myself to the North Atlantic and polar regions, because otherwise I would be speaking for the next 12 hours, I think, and I don't think anybody wants that. So I'll go through what we have learned from vertical measurement, from regional, from local, in situ, from hours to decadal. So it's really, really, really cool to see this graph that was in the paper from 2019, showing the observations from the early 2000s to about a couple of years ago when the paper was published. And what we see here is that the first in situ observation that was carried out by Lee et al. in 2003. It was, of course, built on development of water vapor isotope instruments in the 90s. But then what happened was that around 2008, I checked in older emails that suddenly there was a arrival of these turnkey water vapor isotope measurements. And a couple of years, 1 year later, I was lucky enough to take one of these instruments to the field in Greenland. And from that on, it just really exploded in terms of measurements from all over the world. And I'm I'm sure this could be updated even further today, and you will see even more measurements. So it's really amazing to see how the arrival of a commercial instrument have allowed for a revolution in the field. So what is also important, and I think this is a nice thing to just bring up, especially for our younger colleagues in the field, that actually the development of water vapor isotope analysis were developed initially for a complete different purpose, that being measurement of liquid samples. So I have here 2 pictures of the early liquid water isotope measurement from respectively Los Gatos and the Picaro company. Basically, as you all are aware of, these instruments work by taking the liquid water and creating a vapor stream. So initially, right away, people are like, wait a second, if we're creating water vapor, could we not just take these instruments out and make in situ water vapor isotope measurements? And that was in 2008. However, one of the first challenges that came from this was really to how do we calibrate water vapor isotope measurements? Because there's a fundamental challenge of water vapor isotope calibration, and that being that as opposed to liquid water isotope calibration, you cannot really remeasure the unknown sample again. And in fact, you are treating your sample differently as compared to liquid water, because in liquid water, you have a sample, you can measure it over and over again. You can take it and you can put in your standards and compare it against your standards. For vapor measurement, that's not possible, because of course, when you have done your measurements in the atmosphere, the atmosphere is in a different state. So you need a way to first create vapor with a known isotopic composition, and then you really need to be able to trust that it's comparable to you're treating it the same way, or at least you know what you're doing with it, that you can trust your atmospheric vapor measurements. So I wanted just to show some pictures of the first commercial water vapor isotope calibration units. On the left, we have the water vapor isotope standard source with a schematic below from the Los Gatos company. And from the right, we have the vaporization module from Picaro, in which initially liquid samples was inserted and measured for the isotopic composition. However, I'm not going to go into details on the challenges and shortcomings, but there was a whole development of other custom-built calibration units, which of course has the same principle: take liquid, create vapor, say something that or make sure you know the isotopic composition of the vapor, and you go. So, but in generally, I kind of counted 4 categories of custom-built calibration units. There's the dripper, the nebulizer, the bubbler, and the flash evaporator. The early studies that goes back to the early work of Lee et al. In 2003 was of course using a dripper. In which you simply drip water droplets into a chamber where it evaporates, and you then measure. There was both also development of further development of a commercial system that would allow for more continuous and long-term measurements. Then there's been the nebulizer, which built on a little bit the same principle, but you, instead of dripping the droplets, you create a stream of tiny droplets. I show here a schematic of a system that was actually initially developed for ice core analysis in the CFA system, where an ice core would be measured by melting it and then continually measured it. So of course the observant viewer here would have noticed the gin bottle in a picture, and of course we're not injecting gin into the system, though it might have worked better sometimes, but we needed a place a bottle for waste. So A little bit of similar was the flash evaporator. Here is a picture that I received from Mathieu Casado of his flash evaporator, in which you basically have a droplet, a single droplet existing at the end of a needle or a very, very thin tube, in which you have an equilibrium between flow into the droplet and evaporation from it. This system was also actually developed initially for ice core analysis, but has been further developed for especially going to very low humidity levels that is needed to calibrate instruments when working in the polar regions. And then, of course, there's the bubbler that comes in many different shapes, but it's a little bit different from the three previous mentioned calibration system in that you do not evaporate the water completely, but you assume that you know the fractionation occurring during evaporation, and then you're measuring the vapor. This is a favorite of mine because it has no moving parts and therefore allow continuous operation. In fact, the system that's pictured here is the one from Bermuda that's been running without any incidents for the last 10 years. Of course, you need to know what you're doing in terms of enrichment of your standard and keeping the temperature very stable. But in fact, as you can see just from the figures below from Benetti and my paper in 2017, you do have a very consistent calibration pulse. And that goes, but of course, with some noise, but you can average your way out of that. So, but then we can make measurements with the calibration, but really how do we check, how do we validate our water vapor isotope measurements? And in general, I think there's three ways. So there's a good old cryogenic trapping with half a century of experience behind, in which you simply you trap your vapor in a cryogenic bath, and you then measure it subsequently using either mass specs or other laser instruments, and then you compare with the vapor. But of course, as you're aware of, that it comes with uncertainties in the trapping and in the measurements. So it's not perfect, but at least it gives another way. Then there's the more expensive way is to take two instruments that you calibrate independently, and then that you then compare the measurements against each other. That of course also comes with certain caveats, but it gives you a way of quantifying your uncertainty. So, for example, for the system for the data here that I show was a system where a test I did in Bermuda, where I estimated the uncertainty on the DXS to be about 1.1 per mil in DXS. So quite good. And then there's a new development that I'm quite fascinated about here in the paper by Wozniak in 2021, so fresh out of the press. I'll come back to it as well, is where you actually take samples in a flask that you then measure later. It's a new method. It's still a little bit under development, but it has the potential for especially validating aircraft measurements. So anyway, but let's get to the science and talk about a decade of continuous measurements in different scales. So I'll try to get through them all. I'll have to make sure that I keep a track on my time as well. Maybe I'll get a 5-minute warning. But as I said, it is a medley, and I'm focusing on the North Atlantic and the polar regions. So it's not an exhausted review of all literature out there on this. But as you see, I will go from the vertical, the regional to local, to the site-specific, from hourly to decadal. So let's start with the vertical. So this is a paper that is fresh out of the press from last week by colleagues from University of Colorado, in which we said, what if we, instead of being constrained to the ground, could actually get observations from the atmosphere? And what if we, instead of flying the analyzer on aircraft, instead we took the samples and brought them down to Earth using a drone? So this is what we did. We developed the picture down to the right. It's showing the nose cone from the drone that you saw. Let's see if I can start it again. That you saw being launched here. And in the nose cone of this drone, we have these flasks that would take samples of air from different elevations. The figure below is showing two specific dates, June 12th and June 26th, in which we flew the drone up to 1,600 meters on June 12th, and June 26th up to 500 meters for getting temperature and humidity measurements. And where we also sampled the air for subsequent water isotope analysis on the surface. And what you will see here is that we're specifically focused on the interface between the boundary layer and the rest of the atmosphere, the free troposphere. And we want to understand what is the gradient across this transition. And what you can see here is that with boundary layer and this is of course on top of the Greenland ice sheet, so it's specifically it's quite low compared to what we're normally used to if we're in a more marine boundary layer setting or so on. We make these measurements, found that we assumed that the interface was around in lower 300-400 meters, and we see that we have a transition over just a couple of tens of meters of several per mil in O18. So even though that the isotopic measurements done by this instrument does come with some uncertainty, that is clear, and we hope to, of course, make the uncertainty less. We do have enough signal to noise to actually to see this. So we hope to use this for benchmarking regional and global climate models in terms of how they treat the atmospheric boundary layer. Okay, so moving on to another study in the vertical. This is studied by Benetti from 2008, and with a new figure from Zanoni is in review recently. So this is in this paper, what we ask ourselves: could we, in fact, even though we are constrained at the ground, could we say something about the mixing of the marine boundary layer in this? So what Mario and Benetti did was to develop a framework for studying the mixing processes in a marine boundary layer by saying, well, we know the marine boundary layer consists of evaporation from the ocean plus mixing of free tropospheric air. But we also know from a Craig-Gordon model that the mixing actually changes the isotopic composition of the boundary layer, which will then affect the isotopic composition of the flux. So what you see is that, let's say that we have two end members. S2 is isotopic composition of the vapor in equilibrium with the ocean surface, and S1 is the isotopic composition of the free troposphere. If in fact we were just mixing these two end members without taking into considerations the influence of the mixed vapor on the flux, we would follow the gray line. So this is a simple mixing curve. However, by mixing and taking into considerations Craig and Gordon, we in fact find that the isotopic composition of the flux changes as function of the mixing. And when we plot the delta 18O, the isotopic composition versus the humidity, we find that we had this kind of like S-shaped or banana shape. So for a long time, the model, we called it the banana model, but we thought we had to be a little bit more serious when we published it. So it became the marine boundary layer mix model. And then we're, of course, like, okay, this is very fine with a model, but a model is not really useful if you don't have data. So, of course, we turn to the site in Bermuda, which this site has been running for several years. And we're like, let's try to plot the delta 18O versus humidity, or the DXS versus isotope composition, delta 18O. And what we find is that, in fact, the model actually does capture the variations between O18 and humidity and DXS in a way that is not captured by a simple mixing model. So if we just turn to the right panel, where you can see the DXS versus O18, if it was a simple mixing process without taking into considerations Craig and Gordon's formulation, then it would follow the red dashed lines. Our observations are lying on the dash for the winter, the dashed blue line, and for the summer, the solid yellow line. And the difference between the dashed and the solid line is what isotopic composition we assume for the free troposphere. So in this way, we would have a way to actually give an isotopic composition of the free troposphere vapor on average. And in this this figure, I'm showing how, in fact, we can also say something about the marine boundary layer height. So this is showing the residual between the DXS versus 5 minutes. We have to hurry up. I will have to hurry up. Yes. Between the DXS and relative humidity versus relative, and we see that the residual actually have a link to the boundary layer. Okay, moving on. So if we look to a synoptic and regional scale, we look at the paper by Bonn et al. From 2012. In this paper, we're so lucky that we actually have 3 continuous water vapor isotope analyzers operating, respectively in Bermuda, in southern Greenland, and at Neem up on the Greenland ice sheet. And what we found there was that on June 12th, there was a melt event that was caused by an atmospheric river, and we actually happened to have observations along this trajectory. And the key result here, if I'm just going fast forward here, is really that we observed that the DXS of this vapor that was transported was in fact conserved during transport, which had not been observed before. Okay, then we move to a paper by myself, looking at regional and seasonal variations. So in this paper, we used the year-round observations from the south coast of Iceland on this tower. And what we were able to do is to show that if the isotope versus humidity relationship had a seasonality signature. And of course, we don't know specifically where the vapor come from, so we're just using the existing observations from Bermuda, and we see that in fact the change between the winter and the summer is consistent with changes in the distillation pattern and source region conditions. What we also had from this study was the first indications that the DXS of the Arctic had a very high values. We obtained that by using 2 different sites, EVU2 in southern Greenland and Iceland, and moisture uptake weighted tracking. So moving on and focusing a little bit more on the high DXS, we go to a paper by myself from 2017, in which we took the observations from Svalbard, from Iceland, South Greenland, and Bermuda, and compared with isotope-enabled general circulation model notched to the weather. This is, of course, only made possible with the help of my colleagues, Camille Rissi, Martin Werner, and Ki Yoshimura, who provided the model simulations here. And what we found is, I'm just going to focus on the DXS, so that is the right panel here, was that all the models did actually have biases compared to the observations in in the north-south Atlantic gradient. And they were actually quite opposite. So this is kind of interesting, and it leads me to a point saying that, do we actually simulate the marine boundary layer correctly? And that's what I would like to look further into, because using, on the same paper, what we did was that we also carried out simulations with two different model simulation resolutions, with a zoom version of the LMD set and a non-zoom version of the LMD set. And what we found is that where we saw the largest difference between the two simulations was in the Baffin Bay area. This is what you can see in the color code here, that we see about 3 to 4 per mil differences in the Baffin Bay, and 4 to 6 per mil in DXS. Interesting enough, these biases were exactly the same as what the biases that we saw against the observations on top of the Greenland ice sheet. So from that, we hinted on that the water vapor isotope composition of the Greenland ice sheet, which is very crucial if you want to use isotope-enabled models to say something about, together with ice cores, to say something about paleoclimate variability. What we needed to do is to really focus on DXS in the marine boundary layer. So the first thing I think is important is to notice is that this is a paper from myself in 2014, where we took 500 days of in situ observations in Bermuda, and we compared the DXS versus relative humidity again, and looked at how does the wind speed actually influence? Because as you are aware of, in an old seminal paper from Miller and Chaussel in 1979, we would indeed expect a difference between a smooth regime and a rough regime in terms of the kinetic fractionation. So we would expect that there would be a change in the DXS when we had high wind versus when we had low wind, but this was not observed. Similarly, it was not observed in the result from Bond et al. 2019. So I really encourage you to see the result from our direct isotope flux observation in a poster by Daniela Zanoni on Wednesday. And I will start wrapping up in 2 slides. So the next paper, the next things that I really want to do is to then take the simulation and compare against sensitivity studies of to look at the control on the marine boundary layer. And what you can see here is some 3 different models compared with observations. And I'm just highlighting it's the same result from all the models, but when you show the ECAM DXS versus observed DXS, you see you do not get the high values and the low values. And one of the questions I have is really, is that because of the parameterization of the wind speed effect on the kinetic fractionation? So I think this would be a low-hanging fruit to look into further. Okay. Well, I just want to say, since we do have 10 years of observations, the next study that I'm going to look into is to observe, to use the observed seasonality of DXS versus sea surface temperature that we see in both in observations and in the models, in order to understand the link between large-scale circulations, local processes, and DXS in observations and models. And I would like to point you to the poster by Rosa Olafsdottir today, with 5 years of daily precipitation sampling in Reykjavik. And then I'm starting to wrap up now. Please conclude. Yes. So we have the last paper that I really would like to point to, is the measurement of the direct flux. So this is a paper that was published earlier this year by my PhD student Sonia Wahl. She will also present a poster on Wednesday for the consequences of ice core isotope interpretation, of the fact that she was able to show that with the direct measurements of water isotope flux obtained from eddy covariance and cavity ring time isotope measurement, we were able to quantify the fractionation occurred during sublimation from the snow surface. So, and I will finalize here. with saying that if you want to join an exciting and dynamic research group, I have an open position for a researcher, postdoctoral researcher for 3 years as part of a funded Norwegian Research Council project iTransfer that is going to look at the isotopic transfer rates during kinetic and equilibrium fractionation. So please contact if you have anything. But with that, I want to thank you very much.